Episode 1. From Wastewater to Reuse, the Complete Treatment Journey. Engineering question. How does wastewater move through a treatment system and become suitable for discharge or reuse? 0000. Promise. Wastewater treatment is not one machine, and it is not a magic filter. It is a controlled journey through connected barriers: collection, screening, settling, biology, clarification, polishing, disinfection, residuals handling, monitoring, and finally a decision about discharge or reuse. In this episode, we follow one flow path from a community sewer to a treated water outlet and ask a practical engineering question. How does wastewater become suitable for defined next use without hiding the limits, risks, or operational responsibilities? Before the first basin, the story begins under streets, inside service laterals, gravity sewers, pump stations, and force mains. Wastewater is a variable mixture of domestic flow, commercial flow, and, in some systems, wet weather inflow or infiltration. The treatment plant does not receive an ideal laboratory sample. It receives changing flow, changing solids, changing chemicals, changing temperature, and changing biological activity. That variability is why treatment is organized as a train of unit operations, not as a single universal device. A documented fact: the U.S. Environmental Protection Agency describes water reuse as reclaiming water from different sources, treating it, and using it for beneficial purposes. Jurisdiction note: EPA information is U.S.-based and does not replace local regulations elsewhere. A documented fact from the World Health Organization is that safe wastewater use depends on risk assessment, risk management, health-based targets, and monitoring. A documented fact from the World Bank is that small-town treatment choices should be context-specific, considering facility design, receiving water quality, reuse potential, and operation and maintenance capacity. 0130. Context. The first engineering decision is not which technology looks most advanced. It is the required destination. Discharge to a river, recharge to the environment, irrigation reuse, industrial reuse, toilet flushing, and other non-potable uses can require different levels of treatment and different monitoring. Some reuse applications may involve limited human contact. Others may involve higher exposure risk. The treatment target is therefore not a vague idea of clean water. It is fit-for-purpose quality under the laws, permits, health goals, and operational controls that apply to that location. For this episode, we make one explicit assumption. We are describing a generalized municipal wastewater treatment train for education. We are not designing a specific plant, certifying a product, or stating that one configuration meets any local permit. Real projects must use measured influent quality, hydraulic loading, climate, land availability, operator capacity, energy reliability, residuals options, and applicable discharge or reuse requirements. Where this script uses the word suitable, it means suitable for a defined, regulated, and monitored purpose, not universally safe for every possible use. At the plant entrance, the headworks protects everything downstream. Coarse screens remove rags, wipes, plastics, and other debris that can jam pumps, block channels, damage aeration equipment, or create unsafe maintenance conditions. Grit removal targets dense inorganic particles, such as sand and small gravel, that settle quickly and can abrade mechanical equipment. These steps do not make the water clean. Their job is to protect the treatment process, stabilize hydraulics, and keep avoidable solids out of later basins. After preliminary treatment, primary treatment uses gravity. In a primary clarifier or sedimentation basin, heavier settleable solids move downward to form sludge, while floatable materials such as grease can be skimmed from the surface. The clarified liquid moves forward, but it still contains dissolved and fine suspended organic matter, nutrients, microorganisms, and trace constituents. Primary treatment is an important separation step, yet it is not usually the whole answer when the goal includes robust environmental protection or controlled reuse. 0330. Mechanism. The biological stage is where the invisible labor begins. In many treatment systems, microorganisms metabolize organic matter under controlled conditions. Engineers provide the hydraulic residence time, mixing. After biological treatment, secondary clarification separates the treated water from the biological solids. Some solids are returned to keep the microbial process active. Excess solids are removed for residuals handling. This return and waste decision is a control point.
If too little active biomass remains, treatment can weaken. If too much accumulates, settling and oxygen transfer may suffer. Operators use observations, instruments, laboratory tests, and experience to keep the biological system within a workable range. For reuse or sensitive discharge, secondary treatment may be followed by tertiary or advanced treatment. This can include filtration, nutrient removal, membrane separation, activated carbon, advanced oxidation, or other processes, depending on the target constituents and local requirements. The important principle is not that every plant must include every advanced process. The principle is that each additional barrier must have a defined purpose: reduce particles, reduce pathogens, reduce nutrients, reduce specific chemicals, improve reliability, or protect the end user and the receiving environment. 0600. Application. Disinfection is a final barrier for many discharge and reuse scenarios. Common approaches include ultraviolet light, chlorination, chloramation, ozone, or combinations, selected according to water quality, contact time, safety, residual requirements, byproduct concerns, and operating capacity. Disinfection is not a substitute for the upstream process. Turbid water, poor solid separation, or high organic loading can reduce the effectiveness of downstream barriers. In a treatment train, each stage supports the next one. Residuals are part of the journey, not an afterthought. Screenings, grit, primary sludge, waste biological solids, scum, backwash solids, and concentrated streams must be handled safely. Residuals may be thickened, stabilized, dewatered, disposed, or beneficially used where allowed and appropriate. This episode does not claim any residuals route is universally preferred. The correct route depends on regulations, contaminant profile, land availability, transport, energy, odor management, public acceptance, and long-term accountability. Now imagine the treated water leaving the plant. One branch goes to a permitted discharge point. The receiving water has its own flow, ecology, background quality, and human uses. Another branch may go to a reuse system, where reclaimed water is stored, pumped, distributed, labeled, and monitored for a defined purpose. According to the Environmental Protection Agency, reuse can support beneficial purposes after water is reclaimed and treated. But reuse is not simply turning a valve. It is a whole managed system after the treatment plant. In a reuse system, the engineering question becomes exposure management. Who can contact the water? Could aerosols form? Could cross-connections occur? Is storage protected? Are pipes clearly identified? Are online instruments calibrated? Is there a response plan if quality moves out of range? World Health Organization guidance emphasizes risk management and monitoring for safe wastewater use. The word safe depends on the pathway, the user, the crop or process, the environment, and the controls that remain in place over time. 0830. Limits and risks. A high-quality diagram can make treatment look linear and predictable. Real operations are not always so calm. Wet weather flow can dilute wastewater but increase hydraulic stress. Industrial discharges can introduce compounds that disrupt biology or pass through conventional treatment. Power interruptions can affect pumping, aeration, controls, and disinfection. Seasonal temperature changes can slow or accelerate biological processes. Maintenance backlogs can turn a well-designed plant into an unreliable plant. Treatment is an operational commitment, not just a capital project. There are also knowledge limits. Conventional monitoring often measures indicator parameters rather than every possible contaminant in real time. Some constituents may require specialized sampling, laboratory analysis, or advanced treatment. The absence of a visible problem does not prove the absence of risk. This is why source control, pre-treatment, multiple barriers, verification monitoring, and incident response matter. Good engineering does not promise zero risk. It reduces risk to an acceptable level defined by public health goals, environmental objectives, and applicable law. For small towns, the World Paint Guide highlights the need to select options that match local conditions and operation and maintenance capacity. A process that performs well with skilled operators, reliable power, available spare parts, and strong laboratory support may struggle where those conditions do not exist.
simpler does not automatically mean better, and advanced does not automatically mean safer. The right answer is the treatment train that can be operated, maintained, monitored, and funded for the required service life.
Climate and watershed context also matter. A discharge that is acceptable in one receiving water may be inappropriate in another. A reuse application that reduces freshwater demand may require storage, seasonal planning, or additional safeguards. During drought, reclaimed water may become more valuable. During heavy rain, flows and bypass risk may change. Treatment planning should therefore connect the plant to the larger water system: source water, sewer shed, receiving environment, community needs, and long-term resilience. 11.0 Practical Checklist. Here is a practical checklist for evaluating a wastewater to reuse journey. First, define the destination: discharge, environmental enhancement, irrigation, industry, building reuse, or another specific use. Second, identify the governing requirements: jurisdiction-specific rules, permits, water quality criteria, occupational safety rules, plumbing codes, and public health guidance may all apply. Third, characterize the influent with data, not assumptions. Flow patterns, solids, organic load, nutrients, salinity, industrial inputs, and seasonal changes can alter the treatment strategy. Fourth, map the unit operations and the purpose of each barrier. Screens protect equipment, grit removal protects hydraulics and machinery, primary settling separates solids, biological treatment reduces biodegradable organic matter and can support nutrient transformations when designed for that role. Clarification separates biomass. Filtration, membranes, carbon, nutrient removal, or oxidation address specific advanced targets. Disinfection reduces microbial risk for defined uses. Monitoring verifies performance. Residuals handling closes the material loop. Fifth, examine failure modes. What happens if a pump stops, a screen blinds, aeration fails, a clarifier bulks, a membrane fouls, a chemical feed runs empty, a sensor drifts, or power is lost? The design should include alarms, redundancy where justified, bypass controls, operator access, safe isolation, sampling points, and a clear response plan. A reuse system also needs cross-connection control, labeling, storage management, and communication with users so that a quality excursion does not become an exposure event. Sixth, confirm that the operation is sustainable for the owner. Can operators be trained and retained? Are spare parts available? Is laboratory support realistic? Is energy supply reliable? Are residuals routes permitted and affordable? Are data reviewed, not merely collected? Are public communications clear? This is where the educational diagram meets institutional reality. A treatment plant is an engineered system, but it succeeds through people, budgets, governance, maintenance, and transparent decision-making. 13.30 Conclusion. Let us separate facts, assumptions, and recommendations. Fact: water reuse means reclaiming water from sources, treating it, and applying it to beneficial purposes, as described by the Environmental Protection Agency for the U.S. context. Fact: World Health Organization guidance frames safe wastewater use around health-based targets, risk management, and monitoring. Fact: the World Bank advises context-specific option selection for small towns, including design, receiving water quality, reuse potential, and operation and maintenance constraints. Assumption: the journey shown here is a generalized municipal example. It is not a universal design standard and not a permit determination. Recommendation: start every project by defining the end use and exposure pathway, then design backward through required barriers, monitoring, residuals handling, and emergency response.
Recommendation.